In continuation of the last video on mechanism of organic reactions of BSc Part 1 Organic Chemistry, we will continue with the reactive intermediates. The first intermediate we take up is nitrene. Nitrene is a neutral intermediate species containing a nitrogen atom having one bond pair and two lone pairs. It has an electron deficient nitrogen. Nitrene species are also known as azenes, amines or imidogenes. The simplest nitrene is NH. For example, alkyl nitrene, acyl nitrene, ethyl nitrene and acetyl nitrene. If we consider the formation, then it is seen that the nitrene species are formed by alpha ion elimination, thermal decomposition or by photolysis. If we consider alpha elimination, then we see that alkene amide reacts with bromine and KOH and forms acyl nitrene. By thermal decomposition, acyl azide on heating decompose to give acyl nitrene. If we consider by photolysis, then it is seen that acyl isocyanate when heated with mercury in presence of light gives nitrene plus carbon monoxide. Now we come to the types of nitrines. There are two types of nitrines, singlet nitrine and triplet nitrine. If we consider the orbital structure of singlet nitrine, then we see that nitrogen is in the sp2 hybridized state and one sp2 hybridized orbital forms a sigma bond with a substituent, whereas two hybridized sp2 orbital contain lone pair of electrons and the pure unhybridized p orbital remains empty. If we consider the triplet nitrine, then we see that the nitrogen in this is in sp hybridized state and the one sp hybridized orbital forms a sigma bond with the substituent and the second sp hybridized orbital contains a lone pair of electrons, while the two unhybridized pure p orbitals contain one electron each. Some important chemical reactions of nitrene are as follows. The first one is insertion. Acyl nitrene reacts with alkane to give insertion product. Cyclic addition. Nitrene on reaction with alkenes breaks the pi bond and forms a cycloadduct. Third is rearrangement. It is seen that the nitrines undergo rearrangement reaction to form a rearranged product. Third is dimerization. The fourth is dimerization. It is seen that the two molecules of nitrene dimerize to give a dimer. Now we come to the next reactive intermediate, that is arine. Aromatic compounds containing a formal carbon-carbon triple bond are called arines or benzenes. If we consider the structure, the triple bond of benzene is altogether different from that of the acetylene. In acetylene, it is made up of sp-sp sigma bond and two pi bonds formed by sideways overlap of p orbitals. However, in benzene, the triple bond consists of one sp2 sigma bond and the two pi bonds, out of which one of the pi bond is formed by the sideways overlap of two p orbitals, while the other is obtained by the sideways overlap of two sp2 orbitals as shown in figure. So this is the sideways overlap of the orbital. Since the sideways overlap of sp2 orbital is not good enough, therefore the new pi bond is very weak and hence benzene is a highly reactive molecule, and as they lie sideways, these pi bonds cannot overlap with the electron cloud that is below the ring and above the ring. Benzene intermediate is formed by following reactions. Benzene is formed by the reaction of chlorobenzene and its derivatives with sodamide and liquid ammonia. When chlorobenzene reacts with sodamide or in liquid ammonia, the chlorine is eliminated as the chloride and the proton is eliminated as a proton, that is, the elimination of HCl takes place and benzene is formed. Orthodihalorbenzene reacts with lithium mercury amalgam to form benzene. In this, the fluoro-bromo compound is formed and benzene is result. The third is diazotase anthracite acid on heating in the presence of benzene eliminates carbon monoxide and nitrogen and give benzene. Benzene acts as electrophilic, therefore nucleophile attack on it. Now we come to the energy considerations in organic reactions. The feasibility of any chemical reaction is given by Gibbs free energy change, that is delta G, which is related to the enthalpy change, that is delta H, and entropy change, that is delta S, by the following equation. Delta G is equal to delta H minus T delta S. It may be noted that if the delta G is negative, the reaction proceeds in the forward direction. A positive delta G, on the other hand, suggests that the reaction has a tendency to proceed in the backward direction. Since entropy is a measure of the degree of disorderness of a system, therefore, a system is most unstable when it has maximum entropy. On the other hand, reaction in which there is less of randomness should not be favorable, and it has indeed been found that reactions involving a decrease in the number of molecular species in going from reactant to the products proceed only if the delta H is negative, that is, reaction is exothermic, and also the delta H should be large enough to make the delta G negative. Conversely, when the number of molecular species increase in going from reactant to the product, there is increase in the entropy of the system, and minus T delta S term becomes large enough to make the reaction move in the forward direction even when it is not an exothermic reaction. When the substances are taken in the standard state, for example, at 273 Kelvin and 1 atmosphere pressure, the above equation is as follows. Delta G with superscript 0 is equal to delta H with superscript 0 minus T delta S with superscript 0. Here the superscript 0 is used to denote standard state, and delta G superscript 0 is the difference in between the standard free energies of the product and that of the reactant. However, in case of equilibrium reactions, the equilibrium constant K is related to delta standard free energy by the following expression. Delta standard free energy is equal to minus RT ln K, or minus delta standard free energy is equal to 2.303 RT log K. Here R is the gas constant and T is the absolute temperature. It may be noted that the K denotes the extent of a chemical reaction. A high value of K indicates that the reaction proceeds significantly in the forward direction. Now we come to the collision theory. It is seen that according to the collision theory, their molecules or atoms must come close and collide together to effect a reaction. For example, in this, molecule AB come in contact with B, C, collide and form reaction product. However, all such collisions may not lead to the formation of the product AC and B. For a collision to be effective in bringing about the reactants, it must fulfill the following two conditions. The first is that collisions must take place between the fast moving molecules or atoms so that it provides a certain minimum amount of energy required for the reaction to occur. In other words, the collision must be sufficiently energetic, as we know that if the molecules or atoms are moving with high speed, that means they have high kinetic energy. Secondly, the collision must be head-on collision to have full impact. In other words, the colliding molecules or atoms must have proper orientation with respect to each other. Therefore, the rate of the reaction is determined by the rate at which these effective collisions occur. Mathematically, it can be expressed as follows. Rate of the reaction is equal to rate of the effective collision, or in other words, we can say rate of the reaction is equal to the number of effective collisions per centimeter cube per second. The rate of the reaction will naturally be expressed by change in one or more of the factors, that is, let us therefore consider the changes which can occur by these two factors. First is collision frequency. It depends on firstly the concentration per centimeter cube of pressure in case of gaseous reactions. Secondly, upon the mobility of reactants, which in turn would depend on the weight and temperature. As the size and weight of the reactants are almost invariably constant in a reaction, the collision frequency in a reaction can be varied by changing concentration per centimeter cube of pressure in the case of gaseous reactants and the temperature of the reaction. The second factor is orientation factor. This factor is also known as probability factor. It depends on the shape or geometry of the reactant in a reaction. As each molecule or atom has a characteristic shape, the factor is not very much closely related to the reaction. That's all for today. Thank you.